Thank you for the introduction. Hello, everybody. I'm glad here to present some of my results. I'm currently finalizing my PhD thesis, and I was always also happy to have some good students here doing their bachelor and master thesis who helped me to create these results. And also here my professor friend Walther, they are the co-authors of this presentation. So at first I want to give you some motivation about this interesting topic, and then we will talk about the brazing process to understand the backgrounds. Then we will go to the microstructure to understand the failure mechanism of this material system. And then I want to show you some quantitative microstructure approaches that I developed currently. And finally, we go to corrosion fatigue. So why there's a need for research for nickel-based filamental steel joints at all? I mean, most people don't know these applications. And so I brought you some industrial applications. You can see here the exhaust gas recycling cooler. You can see some turbine components here, brazed honeycomb seals, and also that's quite often used at the moment that are injection mold tools with integrated cooling channels. They are produced in slices and then brazed together. Yeah. All these applications, they have in common that they are under mechanical loads, under corrosive environments, and usually they are operating at elevated temperatures. And that's what nickel-based filamentals are actually good at. But still, there's a limitation of the service life due to corrosion fatigue. And an important factor for this are brittle faces. And where does this faces coming from? Therefore, we have to look into the brazing process. Here you can see the industrial vacuum furnace that I've used. I could braze a lot of specimens at the same time. Here you see the setup for the brazing. I used the metastable austenite AC304L. That's a very widely used stainless steel. And I used here some nickel-based filamental in form of foils. I designed some alloys from the nickel chromium silicon boron system. Silicon and boron are needed to decrease the melting point to make this brazing possible. And also I added some molybdenum and iron to see whether they can change the properties. Finally, then after brazing, some specimens were turned from just standard testing geometry, cylindrical specimens, nothing special here. So now we're looking into the brazing process and try to understand where the brittle phase is coming from. Yeah, it's called diffusion brazing, and that's what happened here. At 1160 degrees, this was the brazing temperature for these specimens I showed you. There, the filamental is completely molten. And then during the diffusion time, during the holding time of the process, there started some diffusion process, especially the light and small atom boron diffuses very quickly and goes into the base material, into the austenite, and forms some chromium borides here at the ground boundaries. But what's happening here is that melting point depression elements leaving the melt, and then the solidus temperature is rising, and so there's starting some solidification. But when the time was sufficient or the temperature was not high enough, there will be some remaining melt, and when we're cooling down here, there can be some hard thermal solidification during the cooling, and this is resulting in these green phases here, some brittle phases. They are called thermal solidification phases, and they are almost chain-like. But when we're looking here to a longer holding time, then we have more time for diffusion, and then we can reach something we call complete isothermal solidification. Then we don't have this these brittle phases here in the center, but we still have in the diffusion zone, in the diffusion affected zone, this chromium borides there on the grain boundaries. So that's for the background, and then I've raised a lot of microstructures. That's just a few of them. you always have the diffusion zone, and there are these dark dots here that are the chromium borides there. And in the center, sometimes you have communication zone phases, sometimes you don't have, depending on the time on the alloy that you have used. So, yeah, what is the influence of these phases? That's an important question. And if you look to fatigue testing, then there's a significant influence of this almost chain-like structure. I've shown you that molybdenum here tends to promote this formation, and this is exactly when we compare filler metal without molybdenum with molybdenum, then we have like a chain-like structure, and this is resulting also in these fracture surfaces. We're looking on the topography. We have on one side we can have a very brittle fracture. On the other side, we can have a more ductile fracture, and this influences the fatigue. You need to consider, I've done the tests here at a ratio of 0.1, so it's creep fatigue, and we have a lot of deformation. And what is important here to consider is the influence of this chain-like structure. This is most visible here at high stress amplitudes, at high deformation, that we need to keep in mind. So, but when we have a good brazed joint without this chain-like structure, a complete isothermal certification, how does the crack propagation looks like then? Because this is actually what we want to have after the brazing process. Then we see that the crack propagates here in the diffusion zone, and what's happening that the chromium borides there, they start to break up and they form micropores, and especially in the near of the crack tip. So there we have a lot of deformation, and then these micropores start to grow, and then we have some merging of the crack tip with the next pores, and this is usually resulting in some kind of zigzag through the diffusion zone, and then going to the solidification zone, going in the diffusion zone again. Because sometimes there are little pores inside the solidification zone from the process. Yeah, that's how it works. And when we come to corrosion fatigue, we also need to consider that we have some microgalvanic corrosion. So these brittle phases can also get critical in terms of corrosion. So just keep it in mind when we come later to corrosion fatigue. So to get a more deeper insight into the microstructure, I did with a focused ion beam some slicing of the brazed joint, and I got a lot of scans inside the scanning electron microscope. Took a long time, and then I used deep learning image segmentation to do some reconstruction of these slices. And then you see this structure here of the chromium borides in the diffusion zone. And you see some other phases. This is not the chain-like structure that I told you before, but this is some phases we could found in this tomography. But the cool thing is now we have a real 3D model. We can turn it around and look through all sides and study it. And what is most important, we have a very cross-linked structure here in the diffusion zone. The phases are almost all connected together, and that's why they start to break up so early under deformation, because they can't move inside the matrix. They are forced to break up when you have the cross-linked structure of brittle phases. Okay, so and what we can also do is segmentation. I'm a fan of microstructure and segmentation, so I decided, okay, we can get from all these microstructures some 2D parameters. I trained some models to get these arch-mode phases and these diffusion zone phases, and I calculated with the Python script like the lengths of the zones and like the numbers of these phases or their area. And when you're doing, you acquire a lot of these parameters, and you have done a lot of tests, like hands-on tests, and you do this with a lot of microstructures. Then you can start to do a lot of correlation analysis. You don't have to stand and say it in detail, but what is important to see that that greener the color, that the higher is the correlation, that you can see that, for example, the accumulated area of this AZ phases, There's a strong correlation, for example, to tensile test to the ultimate tensile strength. Or we can see the same, a little bit lower correlation for load increase tests, for example. This is very interesting, and you can use these 2D parameters for some estimation of the properties. I say estimations because, like you have seen here, for lower stress amplitudes, lower deformation, and higher cycles, there the influence of the brittle phases is going down. Then some other effects starting to work in work, and therefore in future I want to consider also some CT scans, for example, for pores and so on, and then build out a full fatigue life prediction model from these microstructure parameters only. Okay, so now I want to go on with corrosion fatigue, since this is the topic, besides the microstructure. Therefore, I developed a corrosion cell, which was able to do the corrosion simultaneously to the fatigue inside the fatigue testing machine. This cell was designed as a temperature system made from PTFE and some glass only, and I used a 3 electrode system, put some pressure on it to shift the boiling point of the water, so I could do some tests at almost 100 degrees, because these are, if you consider, more or less the real operation condition. If you go to an exhaust gas recycling cooler, for example, and it's not testing at air in laboratory environment. And yeah, when you are doing a lot of tests, it's just fresh experiments here, and you can get that as N curves under creep fatigue, under corrosion creep fatigue. Yeah, we start to look here at different environments. At first on air, and when we add some water into the testing cell, then it decreases slightly, but it could be scattered. It's not such a difference. But when I told you synthetic exhaust gas condensate, it's just on 1 liter water, just a little spoon of sodium chloride and some drops of acid, then it shifts significantly. And I also tried it with 1 molar sodium chloride solution, and it's almost the same. So you see, it just depends on the presence of sodium chloride, if some mechanisms like hydrolysis can start or not. But when it comes to an elevated temperature, then the fatigue life increases even more. And this is all more than a factor of 8 compared to the tests on air. So this makes a huge difference in lifetime. Okay, to understand what's happening there, we will look at these 2 points here. At first, without elevated temperature inside the synthetic exhaust gas condensate, we see the mechanism that we already know. We have seen, okay, these brittle phases in the diffusion zone, they start to break up, they form pores, and also we have these microgalvanic corrosion things. And then the crack initiates, usually in such an area, and then it propagates with some jumps through the solidification zone, through the diffusion zone. That's something you know. But at the elevated temperature, it looks a little bit different. There we have a multiple crack initiation. And yeah, we don't have the main cracks anymore in the brazed joint. So the brazed joint is not the weakest spot anymore. Now the failure will take place in the material. And that was something that surprised me when I did the first experiment, because I thought always the brazed joint must be the weakest point, but here we see the steel is the weak point. But why? We have to look a little bit closer. We see that we have, for example, a lot of crack initiation and intrusions, for example. That's the point where the passive layer breaks up. And this is typically stress corrosion cracking. You have some hydrogen embrittlement and some other stuff that's going on there. And that's why the cracks initiating everywhere. So I will come to the summary. We have learned about the importance of the brittle phases, especially at high stresses and deformations. We know that the chain-like structure is the most critical part. We followed by cross-linked structures. Then we have seen that these broken faces forming micropores. We have seen that quantitative microstructure analysis allowing to estimate properties, and maybe later on we can go into fatigue calculations under certain conditions. And we see that there is a significant reduction in lifetime due to corrosion fatigue, especially at high temperatures when we're shifting it to corrosion, stress corrosion training. Yeah, that's it. And thanks, thankful for the funding and open to questions.